Good morning, everyone. My name is Jingye Li from BIMSA. I'm very pleased to serve as the chair of this session. It's a great honor to begin today's program with a talk by Professor Egor Shelukhin from the University of Montreal. Professor Shelukhin is a leading researcher in symplectic geometry and Hamiltonian dynamics. He has made great contributions to symplectic invariance and group actions, including the recent work on the symplectic Hilbert-Smith conjecture. Today, he will talk about this. Please welcome.
Thank you very much. I'd like to start by thanking the organizers of the conference for the possibility to speak here. It is a great honor for me. And I would also like to thank the audience for coming to my talk on this rainy morning. So I will talk about an exploration of the Hilbert-Smith conjecture in the context of symplectic topology. So to start with, let me remind the audience what is the Hilbert-Smith conjecture. As a way of introducing it, I would like to recall Hilbert's fifth problem. So one of the problems from Hilbert's list of problems from 00, so 1900. So this problem is a topological characterization of Lie groups, a search for such a characterization. So namely, the question is, if a topological group G is a topological manifold, which is it is an inherent property of a topological space, is it true that then G must be isomorphic, well, as a topological group to a Lie group? So is G actually a Lie group? Right? So in particular, is it a smooth manifold, not only topological? Okay? And so this problem was solved completely. So by the efforts of many mathematicians. So for instance, it was answered positively by von Neumann in 1933 for compact groups, and then finally by Gleason and Montgomery-Zipin in around 1955 for general groups, and again, so the answer is yes. So indeed, Lie groups are characterized topologically among topological groups. And maybe one remark, there was also interesting work by Enflo in the 70s, where instead of a topological manifold, namely locally Euclidean space, one requires that the group is locally Banach, so infinite dimensional version. And then there are also positive answers. In the context of Hilbert's fifth problem, let me just say that in 1953, Yamabe proved the following result, which gives a sufficient condition for a locally compact group to actually be a Lie group. And this condition is the following. So a locally compact group is a Lie group if and only if it has no small subgroups. So here, of course, one should be careful, and perhaps no small subgroups should be read as no system of small subgroups. So, so this means that there's an open neighborhood of the identity that contains no subgroup other than the trivial subgroup, other than just the identity itself, right? So, so you know, if groups does not satisfy this condition, then there is a system of smaller and smaller and smaller and smaller subgroups right? Which eventually enter any open set around the identity. Okay. And since this will play an important role later in the talk, let me give the following example of a group which does indeed have a system of small subgroups. So this is the topological group of p-adic integers. So here p is a prime. Okay, so this is the following group. So you consider just the integer z. On the integer z, you have the p-adic distance. Okay, so whereas right, so p-adic distance between a and b is the p-adic norm of a minus b, and the p norm of an integer is well, constant to the minus k, where k is the maximal power of the prime p, which divides the integer. Okay, so here c is any fixed constant bigger than 1, and often one takes just c equal to the prime itself. It's just nicer to do this. Okay, okay, so one has this distance, and then the p-adic integers is the completion of z with respect to this distance. And so Cauchy sequences modulo equivalence. So this is a compact topological group, and furthermore, one can look at subgroups of the form p to the k zp. Okay, so this subgroup is on one hand a closed ball around the unit element, which is 0, right? So it's all the x in zp whose norm is less than c to the minus k, less than or equal to. It's a closed ball. But at the same time, it's an open ball, because it's the same as all x in zp whose p-adic norm is strictly less than c to the minus k plus, let's say, 1/2. Okay, so these are closed and open subgroups, and one can see that they form a base of the topology around 0. Okay, so indeed, this is a system of closed subgroups. Thank you. Okay, indeed, this is a system of small subgroups. And maybe one last thing is that it is convenient to think of the p-adic integers as power series in the prime p. So kind of higher power of prime p means smaller in the p-adic norm, right? So and such power series actually do converge inside zp, and every p-adic number can be written as such a power series. So of course, you know, I said here AI is in Z, so actually, you know, this way of writing a p-adic number is not unique. But I will just need to generate some p-adic numbers. So this is the way to do it. Okay, and now the Hilbert-Smith conjecture. Let me just slide a little bit. The Hilbert-Smith conjecture from 1941. So it is Smith's generalization of Hilbert's fifth problem, is the following question, or statement that one wishes to prove or disprove. So a locally compact topological group which acts on a connected, well, topological, let's say, n-manifold faithfully. So we need to specify things a little bit. So what does it mean that the group acts on the manifold faithfully? It means that it is given by a continuous injection from the group with its topology, it's a topological group, to the homeomorphism group of the manifold. Okay? And homeomorphism group of the manifold is considered with a compact open topology, but so if X is, in fact, let's say a compact and smooth manifold, then we can just say that the continuity is just with respect to the C0 distance. Okay, so one can take any auxiliary Riemannian metric on the smooth manifold. This defines a distance function, d, and then the C0 distance between two homeomorphisms is just maximum of distance between phi of x and psi of x over the manifold. Okay, so faithfully means continuously and also effectively. So so the map from G to homeo of x is an injection. Okay, and so the Hilbert-Smith conjecture is that if you have such an action, then the group must be a Lie group. Okay, so kind of reasonable groups which act on manifolds, on connected manifolds, should be Lie groups, basically. Okay, and maybe another comment that here, so local compactness is basically necessary because, let's say, homeomorphism group of X acts on itself, and homeomorphism group is huge. Yes, it is definitely not a Lie group. And also connectedness is important because otherwise one can take many disconnected copies of a manifold, and maybe of like S1, and then a big torus is going, infinite dimensional torus is going to act. Okay. So this is the Hilbert-Smith conjecture. Unlike Hilbert's fifth problem, the Hilbert-Smith conjecture is mostly unsolved. Okay. So the only results available to us, to the best of my knowledge, about this conjecture as stated are, well, so dimension 1 or 2, so result of Montgomery and Zippin, also works when the action is transitive. So this is very close to the original solution to Hilbert's fifth problem. And also for n equal to 3, so this is a rather recent result of John Pardon. But for n equal 4, we already do not know whether or not this conjecture as stated is true. Okay. All right. But one can still obtain results in higher dimension if one makes one assumption slightly stronger. So instead of homeomorphism group, of the whole homeomorphism group, one can look at actions by homeomorphisms which are slightly more regular than general homeomorphisms. Okay, so one can consider a subgroup of the homeomorphism group, which is defined by certain regularity properties. Okay, so for instance, one can look at a smooth manifold X and look at C2 diffeomorphisms. Okay, so not just continuous, but having two derivatives. Okay, and in this case, the Hilbert-Smith conjecture is true in arbitrary dimension by a beautiful argument of Bochner and Montgomery, which basically uses Taylor expansion, Taylor series. Then this is also known under slightly weaker regularity conditions. So it is enough to assume that the homeomorphisms are Lipschitz. Okay. So this is an argument of Repov-Shepin, which utilizes cohomological dimensions. So it utilizes Young's result on cohomological dimension with respect to quotients by the p-adic numbers. The proof of Repov-Shepin can be generalized to Helder actions with a sufficiently large Helder exponent. So instead of Lipschitz, one requires only Helder. So this was a result of Maleshich. And finally, there's a different regularity property. So the quasi-conformal actions, right? So quasi-conformal means that the norm of the differential is controlled by the Jacobian, by the determinant. Okay. And there was a generalization of Emge in a similar direction. And let me just say that most of the proofs in actually in all cases use the following reduction of the Hilbert-Smith conjecture to p-adic actions. So this is a classical result. So for a given for a given manifold X and subgroup G of the homeomorphism group, Hilbert-Smith conjecture is true if and only if it is true for p-adic integers for all primes p. Okay, so in other words, Hilbert-Smith holds if and only if Zp admits no faithful action. Well, on X by homeomorphisms from the subgroup G. Okay. So I'm trying to slide it a bit, but somehow it's not so easy. It doesn't want to slide. Okay, and so I hope you see the last line here. So the proof of this reduction uses the solution to Hilbert's fifth problem, so the arguments required to do so, and an interesting result of Newman from 1931. So the result of Newman says that the homeomorphism group of a manifold has no small finite subgroups. Okay? So this means that there is a neighborhood of the identity which contains no finite subgroups other than the trivial one. So when one takes these two ingredients together, one can prove this reduction. Okay. So this is about an introduction to the Hilbert-Smith conjecture. Okay. Wait a moment. Okay. So today I would like to discuss Hilbert-Smith conjecture, but by actions for actions by homeomorphisms of a certain symplectic nature. So one can consider these as a non-standard regularity condition on homeomorphisms. So let's very slowly see what are these symplectic homeomorphisms. So first of all, consider a closed symplectic manifold of dimension 2n. So 2n for me will always be the dimension of a symplectic manifold. So omega is a closed non-degenerate 2 form, which by result of Darboux is the same as saying that it looks as just some dpi wedge dqi in suitable local coordinates around any point. Okay, so this is the standard symplectic form on the standard phase space. Okay, and perhaps for this talk, one can just think that our closed symplectic manifold is the standard symplectic torus. Okay, so one looks at the 2n torus, right? So it's R over Z, it's a circle to power 2n, and the symplectic form is just some basically dpi dqi I just called by rho I and theta I the angular coordinates on the ith T2 component. So you can think of this T2n as T2 to power n. And on every T2, there are angular coordinates rho I and theta I. So this is the standard symplectic. Okay. So before discussing homeomorphisms, let us briefly discuss two groups of symplectic diffeomorphisms. So given a symplectic manifold, one has the Hamiltonian group of the symplectic manifold and the identity component of the symplectomorphism group. Okay, so of course both of them are subgroups of the diffeomorphism group of the manifold, but for the purposes of this talk, it's going to be convenient to consider them as subgroups of the homeomorphism, which is of course large. Okay, so first of all, what are Hamiltonian diffeomorphisms? These are time-one maps of Hamiltonian flows, which is to say you consider a smooth function on the manifold, which depends on time and is one periodic in time. Using the symplectic form and the Hamiltonian function, one can construct a time-dependent vector field. And then this time-dependent vector field generates an isotopy phi th, and you take the time-one map. So when you run over all the Hamiltonians, you get a subgroup of the diffeomorphism. And these diffeomorphisms are to be considered as generalization of the notion of just like motions of classical mechanics, right? So locally, in local coordinates, pi and qi, so this equation is just Hamilton's equation, p dot equal minus dht dq and q dot equal dht dp. Right. And the identity component of the symplectomorphism group, which will be somehow mentioned less in this talk, but still, it is just the identity component of the group, of the subgroup of the diffeomorphism group, which preserves the symplectic form. Okay, so these are just time-one maps of isotopies starting at the identity. Isotope is psi t, such that psi t star of omega equal omega for all t. Okay. And this is a slightly bigger group than Ham, and you can just so it's a classical result that sim 0 of Ham is isomorphic to a quotient of H of the first cohomology group, so finite dimensional, in fact, finite dimensional vector space of R, quotiented by a certain subgroup, and this subgroup called the flux group was proven by the efforts of many mathematicians, for instance, Lalonde, McDuff, and Poltrovich in certain cases, and finally by Ono in 2006 in complete generality. So it was proven that this subgroup is a discrete subgroup. Okay. So basically, sim 0 of a Ham is a finite dimensional Lie group. Okay. Now, for homeomorphisms, let us take the following definition of Bukovsky, Miller, and Seifadini from 2018. So Ham bar inside homeo is just the C0 closure, the closure with respect to the C0 metric of Ham inside homeo. Okay, so consider this closure. So elements in this closure are called Hamiltonian homeomorphisms, right? And these are those homeomorphisms that can be C0 approximated arbitrarily well by Hamiltonian diffeomorphisms. So this is the regularity condition that you can approximate. Okay. And then these homeomorphisms satisfy certain flexibility and certain rigidity properties. So for instance, an interesting result of Bukovsky, Miller, and Seifadini says that if the dimension of the symplectic manifold is 4 or more, then there exists a Hamiltonian homeomorphism of M with just one fixed point. So, but in general, for smooth Hamiltonian diffeomorphisms, let's say if the second homotopy group of the manifold is 0, by all the results of Hofer and Floer, let's say the smooth diffeomorphism has at least n plus 1 fixed points. One can sharpen it in various ways. One can replace this n plus 1 by the cup length of the manifold plus 1. One can replace it by, in fact, by the Lusterling-Schnirelmann category, indeed, if pi 2m is 0, so result of Rudiak and Oprea. In any case, so this is a flexibility property. One can kind of collapse all the fixed points into one, which is impossible in the smooth case. Another manifestation of flexibility is the following classical example of a Hamiltonian homeomorphism. So consider a function on the open interval 0 epsilon with values in the real numbers. So I wrote here real positive numbers, but in fact it's not so important that they're positive. And let's say that this function is 0 in a neighborhood of epsilon. Okay. But near 0, it can be very, very wild. It can oscillate, it can grow super fast. Okay. But no matter how wild this function lambda is near 0, if we take the function lambda of norm z squared on Cn, this still generates a Hamiltonian homeomorphism with a compact support. Okay? The idea is that where lambda starts behaving more and more wild, becomes having smaller and smaller support. So in C0 topology, this still makes sense, still converges. Okay, so okay, and then by Darboux theorem and Darboux coordinates, every symplectic manifold locally looks like Cn. So one can implant this Hamiltonian homeomorphism inside any symplectic manifold. Okay, so this means that Hamiltonian homeomorphisms satisfy no classical regularity properties. Just because one can make this lambda explode really, really fast. So all derivatives explode at some enormous rate, and so no classical regularity properties hold. Okay. However, Hamiltonian homeomorphisms satisfy also certain rigidity properties. So for instance, if, again, pi 2 of m is 0, and we have a symplectic ball inside the manifold, so it's let's say an open subset, which is symplectically diffeomorphic to a ball of radius r inside Cn. So there's a diffeomorphism from B to this Br, which preserves the symplectic form. Okay, so it's a symplectic diffeomorphism. Okay, so if we have such a ball of kind of symplectic radius r, then a Hamiltonian homeomorphism displacing this ball, so phi of the closure of B intersect the closure of B is empty. So such a phi cannot be too close in the C0 distance to the identity. So the C0 distance of phi to the identity is at least r squared divided by a certain constant depending only on the manifold. Okay, so this is indeed a certain rigidity property. Okay, because in principle, one can make this ball very, very thin and just displace in the transverse direction. C0, this would not do much for the norm, but for these Hamiltonian homeomorphisms, this cannot happen. One cannot do it somehow magically. Okay, and so these homeomorphisms satisfy certain other rigidity and flexibility properties as well. So there was work of Buchowski and Obstein about this, for instance. And so this will be the main group of interest for this talk. Okay. However, one can also consider the C0 closure of SIMP0. Okay, and this will be a slightly larger homeomorphism group. So, okay, why doesn't it? Okay. So this brings us to the main result of this talk. So the result is the following. So consider a closed symplectic manifold. so compact without boundary, assume that pi2 of the manifold is 0. So for instance, one can think again of the standard symplectic 2n torus. Okay, then the Hilbert-Smith conjecture holds for the group of Hamiltonian homeomorphisms. Okay, so there are no faithful actions from the p-adic group to Ham bar. There, or in other words, by this reduction argument that we saw before, this is the same as saying that if G is locally compact and it admits a faithful action via Ham bar, then G must be a Lie group. Okay. In fact, slightly more can be said in this situation, and I will make a comment about this in a moment. Okay, so this is the result. Let me just say that there are certain generalizations of this result possible. So, for instance, I assumed here that pi2 of m is 0. Actually, it is enough to assume slightly less. It is enough to assume that omega on pi2 is 0, and also C1 on pi2 is 0. Okay, so these are the so-called symplectically aspherical manifolds. So somehow, for the purposes of symplectic topology and Floer theory, such manifolds are as good as aspherical. Okay, and furthermore, with my student Margudiev, we could also prove the same statement for other symplectic manifolds, for instance, Calabi-Yau manifolds. Now, a few remarks. So first of all, using joint work with my former student Marcelo Atala, we could also prove that the Hilbert-Smith conjecture holds for sim0 bar for certain symplectic manifolds. So not all closed aspherical, but for certain ones, for instance, for the standard symplectic 2n torus, or more generally for just products of surfaces of genera 1 or more. Of course, if all the genera are 1, you get the standard symplectic 2n torus, but one can do slightly more. And one reason I am mentioning this is that in particular, this allows us to recover the original Hilbert-Smith conjecture in dimension 2. So for surfaces of genus 1 or more, by a certain procedure of averaging the measure along the p-adic action. And maybe one last remark is that via work we did with Nicholas Wilkins, in fact, in the setting of the theorem, ZP not only admits no faithful Ham bar actions, it also admits just no continuous Ham bar action. Okay, so every continuous Ham bar action of ZP on a closed symplectically aspherical manifold must be just the trivial action. Of course, trivial action always exists. Yeah, so you can just let every element of your group act by identity. No problem. But it does not have any other one. And the difference between the main theorem and this strengthening is that we rule out finite actions as well. So finite actions, I mean, so we rule out actions by finite groups. In fact, finite cyclic groups, in fact, it's enough to look at groups of prime order. Okay, and this implies the following, in particular. So if a locally compact group G acts faithfully via Ham bar, closed symplectically aspherical manifold, then okay, we already know that G must be a Lie group, but in fact, it is also a torsion-free Lie group. And torsion-free Lie groups are quite rare. So for instance, torsion-free Lie groups must be contractible. Okay, and using this, one can show that if this action actually lands inside the smooth Hamiltonian diffeomorphism group, then identity component of G must be just Rk, the additive group of Rk for certain K. And these always exist. This is not hard to construct. Right, so one should remember that we look at closed symplectically aspherical manifolds. So of course, on other symplectic manifolds, you have other Lie group actions. Okay, okay, and perhaps another type of results one can obtain with respect to these p-adic actions is the following. So instead of looking at Hamiltonian homeomorphisms, let's just look at smooth Hamiltonian diffeomorphisms. Okay. In this case, celebrated geometric structure introduced first by Hofer for R2M, and then somehow here's a result first proved by Hofer in that case, then generalized by Viterbo, Polterovich, and finally by Lalonde-Macduff in complete generality, is that this formula, which I will review in a moment, gives a conjugation invariant norm on the Hamiltonian group. So it's a norm on this group. In particular, it satisfies the triangle inequality. It is symmetric with respect to taking the inverse. And it is a genuine norm. It is non-degenerate. So if phi is not the identity, then this norm of phi is strictly positive. Okay. So the formula is as follows. So you take a Hamiltonian, so this time-dependent function, generating phi. So the time one map of the flow determined by h is phi. Then you consider maximum of the Hamiltonian at time t minus minimum of the Hamiltonian at time t. This is the oscillation of the Hamiltonian at time t, and you integrate it from 0 to 1. So this is a celebrated norm of symplectic nature. And so a second result is that if M omega is again closed symplectically aspherical, then there are no actions of ZP via the Hamiltonian group, the smooth one, which are Hofer continuous. Okay, so the continuity changed. Okay, and this theorem is interesting for the following reason. So as a consequence, one can prove the following beautiful result of Leonid Polterovich. So if one considers certain p-adic Lie groups, so compact simple p-adic Lie groups, then these ones admit no homomorphisms whatsoever to the Hamiltonian group. Okay, again under the same assumption. And one might think that theorem C is just the same as theorem B. Actually, it is not, because here we make no continuity assumptions. Okay, so there are just no kind of homomorphisms, just algebraic homomorphisms. Just they do not exist. Okay, other than the identity, of course. And what happens is that since the Hofer norm is conjugation invariant, there exists a beautiful automatic continuity result of Polterovich, Shalom, and Shem Tov for such Lie groups. So the way you prove this result is you first say that every such homomorphism must be Hofer continuous, and then this p-adic Lie group admits a copy of the p-adic integers, just in the neighborhood of the identity. And then you apply theorem B. Okay. Finally, I must say that working harder, one can extend this theorem C to actions by Hamiltonian homeomorphisms. You might have wondered why here it is smooth, and in the main theorem it was just homeomorphisms. Well, here you can actually extend it, but this requires further work. Okay, so this is all I wanted to say about the results. So now, perhaps, if there are no questions, I might continue to describe a few of the ideas of the proof. So I will describe them carefully in a moment, but maybe I should say the following. So the proof involves the classical package of quantitative symplectic topology, in particular C0 symplectic topology, plus one new ingredient from Floer theory concerning iterations of Hamiltonian diffeomorphisms, and a new idea which is specific to p-adic integers. Okay. So very briefly. First of all, Floer, so as observed by Viterbo, Schwarz, and O, Floer homology, right? So Floer homology, where for a Hamiltonian, we can introduce the symplectic action functional on the contractible loop space and consider basically Morse theory for this action functional. This has its formal difficulties, but they can be overcome as first observed by Floer. And consider a complex which is quasi-isomorphic to just the homology of the manifold. And then using this complex and the filtration on it given by the action functional, one can cook up these spectral invariants. So spectral invariant, for instance, of the Hamiltonian, of the fundamental class with respect to a Hamiltonian is the infimum of action levels such that the fundamental class is represented by a cycle in this complex with action filtration at most A. Okay. There is also a coefficient ring or coefficient field in the background here. I will mostly ignore it, but in fact it is an important point of the arguments here. Okay, so second ingredient in the package of filtered Floer theory, where now this coefficient ring must be a field, is the following observation we made with Leonid Poltorovich. So for every Hamiltonian diffeomorphism, there exists a barcode. So a barcode is a multiset of intervals. There are finite intervals and infinite intervals towards the positive real direction. So either interval AB or interval A infinity. And okay, this map is continuous in suitable distances. For instance, on Ham, one can take the Hofer distance. And on the barcode, the bottleneck distance between barcodes. Okay, so perhaps I should say that a bar AB means that at level A, there is a new cycle being born, and after B, the cycle disappears. Okay, and using this interpretation, one can think of what it means to look at the sub-barcode of degree I. So sub-barcode of degree I, so it is exactly those bars, those intervals, which correspond to the birth of a degree I cycle, okay, which later disappears. If it's a finite bar or does not disappear at all if it is infinite. Okay, and then the barcode is just the union of the degree I, barcodes over all degrees I. So Furthermore, in what relates to C0 symplectic topology and Hamiltonian homeomorphisms, it was proven by Bukovsky, Miller, and Seyfadini under the assumption of symplectic asphericity, but okay, let's say that pi 2 of m is 0. By now, there are some generalization. So the spectral norm, gamma of phi, given by spectral invariant of fundamental class with respect to Hamiltonian plus spectral invariant of fundamental class with respect to the inverse Hamiltonian, generating the inverse Hamiltonian diffeomorphism. So the spectral norm is continuous in the C0 topology, extends to Ham bar, and is in fact a conjugation invariant norm on Ham bar. Okay. Furthermore, it is going to be useful to say the following two things. First, in a sufficiently small C0 neighborhood of the identity, the spectral norm is Lipschitz with respect to the C0 norm. So gamma phi is basically less than the C0 distance of phi to the identity. There's a constant, but we can normalize it to be 1 if we wish. Another point relates to the non-degeneracy of this norm. So why is gamma phi positive when phi is not the identity? Actually, I have a typo here. It should be not identity. Okay. So if phi is not identity, it means that it displaces a small ball in the manifold. Okay. So there's a ball, let's say B bar, such that phi of B bar does not intersect B bar. And if this B bar is symplectomorphic to a radius R ball inside Cn, then the spectral norm of phi is bigger than some constant depending only on phi and not on any sort of coefficients, which is bigger than pi r squared. So pi r squared is what's called the symplectic capacity of this ball of radius R. Okay. And finally, together with a result we proved with Asaf-Kislev, Bukovsky, Miller, and Seyfadini could prove that every Hamiltonian homeomorphism also has a barcode, which is well defined up to shift and continuous in gamma, in this norm gamma. And furthermore, absolutely crucially, for all positive epsilon, the number of bars of length strictly bigger than epsilon in the barcode, so this number is always finite. So this is a regularity property with respect to Floer theory of Hamiltonian homeomorphisms. So this regularity property is exactly what we will violate in the case of the existence of faithful action by the periodic integers. Okay. So let me just introduce two useful notions. So first of all, Bi of phi consists of bars. Okay? And we can look at the maximal length of a finite bar in Bi of phi. So let's call it beta I of phi. And then the maximum of all of these Bi phi, it actually exists, is what's called boundary depth. This is a notion introduced by Michael Asher. But somehow, for the argument I will present in a moment, this beta I, which depends on the I, is important. And finally, let me just say that all of these lengths of finite bars are controlled by the spectral norm. So beta is less than gamma. Okay, so this is what we need from the classical package of quantitative symplectic topology. Now, for the two non-standard ideas, first we have the following what I like to call iteration inequality. So it is one thing we can say about the barcode and the spectral norm of Hamiltonian diffeomorphisms, and actually homeomorphisms, under iteration. Okay, so, so here's what one can prove. Suppose we have a Hamiltonian homeomorphism psi, and we want to look at the spectral norm of psi to the A. There's a little technical point here. Here, A is a prime, and the coefficients are exactly of characteristic the same prime. In any way, so we look at spectral norm of psi to the A. So this wants to grow linearly in A. So this wants to be bigger than A times the initial norm. But of course, this is not always the case. One can actually give examples of Hamiltonian homeomorphisms such that the spectral norm of any iteration is uniformly bounded by 1, let's say, for the number 1. Okay, so clearly, if such an inequality has any chance of holding, there will be an error here, and this iteration inequality, which is proved using equivariant Floer theory and quantum Steenrod operations, provides a candidate for what the error is. So this is an upper bound on the error. One can do slightly sharper than this upper bound, but this is sufficient for the talk today. Okay, so it is given by a sum of this beta I of psi to the A, this beta I that I defined here. So maximal length of a finite bar of degree I, okay, over an interval of indices which is linear in A. Okay, actually this is not really interval, this is 2 intervals, but anyway, the total number of degrees here is linear in A, around 4NA. Okay, so this is the new input from Floer theory, the iteration inequality. And furthermore, the general idea about p-adic integers is the following. It's pretty simple. So the idea is that if we have a continuous action by p-adic integers, then these small subgroups of the p-adics give us large roots of certain elements in the image of the action. Okay, so small subgroups give large roots. Okay, so to explain this idea, let's start with a little warm up. So the warm up is that if we have an integer a, let's say, that is not divisible by p, so it is not 0 modulo p, then this integer is invertible in the p-adics. Okay, so kind of in the integers there are not so many invertibles, right? So it's just plus and minus 1. But in the p-adics there are many invertibles. You just need the first term modulo p to be invertible, modulo p. Okay, and maybe another point is that the p-adic norm of the inverse is the same as the p-adic norm of the A here, and it is 1. Okay. So this is the warm up, and now let me just briefly say this. Briefly describe this idea more precisely. So we have a continuous action of the p-adics by some, let's say, group of homeomorphisms with a norm. So then, then we get roots of the topological generator of the image with large norm. So how do we do this? We say, well, let's consider this small subgroup P to the k ZP, where k is very large. By continuity, the image of this subgroup will have small norms. So every element in the image of the subgroup will have very small norm. So it's this delta k, which can be made arbitrarily small. But then we can consider a number which is, let's say, 1 modulo p to the kz, just an integer. This one can be inverted, and it is still 1 modulo p to the k in the p-adix. Okay, so it is still something of the form 1 plus something very small. Okay, so then we can consider rho of this A inverse. And rho of this A inverse, again, it's A inverse is something of the form 1 plus very small. So norm of this will be bigger than norm of rho 1 minus something very small, minus this delta k. Okay? And furthermore, just by calculation, we see that rho of A inverse composed A times is just rho of A inverse times A, which is rho of 1, which is our topological generator. Okay, so we got psi, which is rho of A inverse, is the eighth root of phi, right? And its norm is very large. So it's roughly the same as the norm of phi. Okay, and finally, an observation that here one can work with a prime by Dirichlet's theorem on arithmetic progressions, because 1 and p to the k are coprime. So there are infinitely many primes which are 1 modulo pk. Okay. And I described the ingredients in the proof, but here is the proof itself. So one can use the previous idea to construct roots, eighth roots, psi of our phi. And the phi we can assume is pretty small, such that the gamma norm of these roots is bigger than a constant depending only on phi, strictly positive. And finally, when one plugs this idea into the iteration inequality, one gets the following. So A times the spectral norm of the root psi, okay, is bigger than A times some constant that depends only on phi but not on A. Okay, it's strictly positive, so this grows linearly in A. So the left-hand side must also grow linearly in A at a rate which is at least epsilon phi over 2, this constant. And then we just observe that, okay, here you have a linear number of terms in A. Each one is uniformly bounded by some constant. Right? And it grows linearly in A with a certain rate. So this means that the number of terms which are bigger than a very small number, depending on this epsilon phi and delta, must grow to infinity actually linearly in A. But on the other hand, it's not hard to show that this must be bounded, because in fact this psi was the eighth root of phi. So psi to the A is phi. It is a fixed homeomorphism. Okay. So then indeed we have violated the regularity property of the Hamiltonian homeomorphism. Okay. So here I just included a slightly more careful estimate proving that this n prime of phi must grow. Okay, so which atom one should choose? Well, one should choose eta such that 4n eta is less than epsilon over 2. So rate is smaller. And that's it. That's it for the talk. Thank you very much for your attention.
Any questions or comments? Professor Egor Shelukhin gives the detail of the proof. If someone interested in this problem, you can work out on it. Okay, if there's no question, let's set out again.
Thank you very much.